In this case, let us say delta B and delta C are the consistent, kinematically consistent displacements. Let us look at that particular body, rigid body. This is B, this is C, this has moved by, let us say the position of this is xc yc, okay, and it has moved. In this particular case we know it has moved like this. Let us denote the movement by delta xc delta yc, alright. In a similar way I can denote this point to be xb and yb, and let the movement be delta xb delta yb, alright. Now how do I find out the virtual displacement at any point in between? That is not very difficult. There is a straight rigid body. I just have to do an interpolation between these two, as simple as that. For example, if I take this as anchor and wish to find out at a particular point, for example in this case I want to find out at the midpoint, okay. Let us say this length is L, okay. Then it is simply delta xb, I have to add the appropriate difference. For example, in this particular case delta xc, so this is delta at x at p is equal to delta xb plus the gradient of that virtual displacement, which is nothing but delta xc minus delta xb by L times the appropriate length. For example, this is L by 2, I know it is L by 2 and therefore I have to apply L by 2 here, okay. Very simple, it is just a linear equation that we are using here, linearly interpolating it, and therefore we will get this to be delta xb plus delta xp into L by 2 by L, which is delta xb by L minus, and therefore we will get delta xb by 2 plus delta xc into L by 2 by L, which is delta xc by L by 2, I am sorry, is equal to delta xb plus delta xc by 2. Right. Similarly, if I have to find out the virtual displacement in the y direction, I will get it to be delta yb plus delta yc divided by 2. The reason why I am telling you this is it may be worth it finding out the displacements of the ends of these bars, okay. Once I find out the end displacements, virtual displacements, it is possible to find out at any point in between. So if there is a force acting here like this, if I know this length with respect to the total length, it is very simple to find out the virtual displacement at this point, and I can use that for this active force, alright, and this should be clearly understood again, okay. And therefore the bottom line is I need to find out the displacements at each of the salient points of the rigid bodies, okay. Sometimes I may have a hinge and this may be extending like this, so it is better that I find out here because this is connected at this point, okay. As long as this is clear, we should be able to solve this problem. One more important thing before we solve the problem that we started up yesterday. Let us say in this exercise I wish to find out the reactions at C. How many reactions are possible? Let us just start with the problem as such. We have two pinned supports here, it is a pinned joint over here ABC, as we know already. I am just not denoting the external forces here. If I have to find out the reactions here, there are two reactions. One reaction I can say is vertical, right. So if I remove this pin joint, I have Cy and Cx. I need to find out both these reactions. If I need to find out both the reactions, what can I do? In the earlier exercises that we have carried out, we only said you release one of them. In this particular case, I have released two of them. What shall I do? The answer is not very difficult. Well, apply two virtual displacements. So, one virtual displacement along this direction and another virtual displacement along this direction. Okay. The question is, can I? The answer is yes, because the number of degrees of freedom for this system is 2. I have released two of them here. Originally the degrees of freedom were 0. When I released one of them, degrees of freedom became 1. When I release 2, it has 2 degrees of freedom, which means I can specify two values, one independent of the other, as displacements at any single point. Okay. Is this point very clear? Okay. So, in which case, in this particular body BC, I can specify a displacement in the x direction. Let us say this is delta xc and delta yc independently, and seek to find out the virtual work, seek to apply the virtual work principle, so that I can write equations of equilibrium. Well, I have two of them, what shall I do? Okay. We will answer that question subsequently, but to just give an answer immediately, I would only say that if you group the terms related to delta xc and terms related to delta yc, you have two terms that can individually go to 0, because this is independently specified and this is independently specified. So, if I have something times delta xc plus something times delta yc equal to 0 as a result of virtual work principle, this means since this is arbitrary and this is arbitrary independently, each of these terms have to go to 0, which means I will get two equations of equilibrium from which I can solve the entire problem. And therefore, depending on the number of degrees of freedom, you will be able to apply that many virtual displacements. Is this clear? Usually it is a little cumbersome if you go to too many number of degrees of freedom, but it is possible to do, and that is what is done in the popular methods such as finite element methods. Okay. So, we will go back to the problem that we were looking at. I am going to use only the line diagram now that you are familiar with the line diagram. If I remember correct, they had self weights like this, right. The self weights were for homogeneous state members for this and this. The problem was to find out the vertical reaction at A. To find vertical reaction at A, that is the problem, am I right? Okay. So, what should I do? Naturally, since I need to find out this vertical reaction, I have to release the vertical displacement of A and substitute with the reaction. Mind you, this is a notion that I have inserted. The vertical reaction could be this way or this way. If I have assumed like this, just as in equilibrium equations, I will get a negative value if the actual direction is the opposite. Okay. Since I should not allow movement in this, I will have the horizontal displacement arrested at A. I need now give a virtual displacement. Okay. It is not necessary I have to give a virtual displacement here, I can give virtual displacement at any point. Okay. This is a difficulty you will face, you can give it at any point, it does not matter, you will get the same equation of equilibrium. For now let me just give a vertical displacement here and find out the appropriate virtual displacements. So let me give a virtual displacement here, I am going to give a direction and this is delta y at A, alright. Now I have not done something, what is that? I have to fix the reference coordinates. Okay. I know this is a fixed frame of reference and therefore I will use this as a positive notion, it does not hurt using this is x and this is y. What is the displacement of C? It is always 0. We have to be consistent with the way in which they have been arrested, displacements have been arrested and the movements are possible. Delta xc is equal to delta yc is equal to 0. The virtual displacement, whatever displacement I give anywhere, the virtual displacements at C are equal to 0. Okay. So and it is a nice reference to use because these are 0. Now I have given delta ya, what I need to find out are the virtual displacements at these 2 points, especially vertical virtual displacements. Okay. Once I have those vertical displacements at virtual displacements at these 2 points, let me call them as P and Q, then I can write the virtual work equation. So the aim is to find out these 2. But please remember, as I had mentioned earlier, this is one rigid body, this is another rigid body. So I should seek to find out what is the virtual displacement of B, so that I can find out the virtual displacements of P and Q. Okay. So that is the way we have to go about. What is the virtual displacement of A along the x direction? It is equal to 0. Why? Because it is not allowed to move the direction. Okay. This is already known, delta ya is specified, delta xb and delta yb to be found out. Okay. This is the problem. Now how do I go about doing this? Let us just look at the geometry. For now let us assume small displacements. So small variations is what I am trying to find out. Okay. This is xb, yb, this is xc, yc. For now I am going to take a 0 0, right. This is the positive notion, this is the positive notion, and this is yb, I am sorry, xa and ya, okay, because this point is A. What do I know about the lengths here? This length is equal to 1, which is already specified, 1 meters, and this is also 1 meter. Okay. The x displacement of this particular xa is equal to 0 and the distance between this is also specified as 1 meter. So let us look at those which are unchanged during the virtual displacement. What are the unchanged or unchanged lengths? This is very useful to start with. What are the unchanged lengths? AB, length AB, length BC, and the other one also is something I know, length AC. So I can make use of these in the geometry in order to write down relationships between these points xa, xb, ya, yb. Okay. The simplest thing I can do is use the geometry here. Let us say this height is h. What is h equal to? If I take with respect to this, yb is given by h directly, right. What I am doing right now is this right hand side, let me call this as D. So, I am looking at the triangle BCD. Okay. I know height is yb is a positive value, please remember this is the direction yb. And how about this length? This length CD is equal to xb, greater than 0, greater than 0. Clear? Now, what is this length BC? It always remains, the length here is root of xp squared plus yb squared, that always remains the same. Okay. So, let me use that fact. What do I have? Since this is a right angle triangle, I have right angled triangle BCD implies xb squared plus yb squared is equal to 1. Whatever I do, you notice that there is a right angle that I can maintain, this is xb, this is yb, and therefore this relationship is going to hold good irrespective of whether there is a movement that has occurred to b. Okay. I have made use of that particular fact. Okay. I also know that I am going to move by a very small amount, virtually move by a very small amount, and therefore, if I can take a derivative of this, I will get 2 xb delta xb, where that is the small variation, plus 2 yb and times the variation of yb is equal to variation of 1, variation of 1 is 0, and I get a relationship like this. Okay. This tells me that the variation of xb is related to variation of yb through this relation. Immediately we can write this to be minus of yb by xb times delta yb. Okay. That is simple. In this particular case, when I start from this particular configuration, I know the height and the base is half of 1 meter, which is 0.5 meters, and the height is root or immediately I will get it to be root of 3 by 2, right. So, I can use this over here directly. Okay. So, what do I get here is equal to root 3 minus root 3 times delta yb. What does this mean? This means if I start from a configuration like this, where this height is given by root 3 by 2 times the hypotenuse, correct, and this being half of 1 meter, then this is the relationship I get. Please remember that very clearly. Supposing I had used some other configuration to start with, this will change, and therefore this holds good all the time. This holds good only for the configuration I start with here, which is given by yb equal to root 3 by 2 and xp equal to half, and that is how we get this relationship. Please remember that it is only applicable for small displacements. If it is not so, I have to use this. I still can use virtual displacements, virtual displacement equation, but if I use this, it is for even larger displacements. Okay. Now, having found out this, we have found out only the relationship between xb and yb virtual displacements. We need to somehow connect this xb and yb to delta ya, which means we need one more relationship between delta ya and xb delta yb. If we once we get that, we are done with that. So let us look at this configuration. Again, if we take the left hand side right angle triangle, AB remains unchanged, okay, and in this particular configuration that we see, the height remains root 3 by 2 and this base remains half. Okay. So let us write down the relationship. So I have B here, A here, okay, and this is 0.5, this is root 3 by 2, let me write this as half meters, okay, and I have xb here, xa here, okay. Is xa greater than xb? The answer is yes. So if I write xa minus xb, that is a positive quantity which is this length, okay, and how about this? This is y b is greater than ya, so I will write it as yb minus ya, so that I am handling only the positive values, okay. I will do the other way and show you that you will get a wrong relationship and you have to be careful that you take the positive quantities. So this square plus this square for a right angle triangle should give me the hypotenuse square, which is equal to 1 square. Just like the previous example of geometry, we have now for the triangle ABD, we get this, okay. Again, if we need to find out the relationships between the virtual displacements, I need to take the variation of this, which is nothing but 2 times xa minus xb. Mind you, this xa minus xb according to the geometry is a positive quantity, times delta xa minus delta xb plus I have 2 times yb minus ya times delta yb minus delta ya is equal to 0, okay. What has we achieved here? What have we achieved here? We have achieved a relationship given xa minus xb and yb minus ya according to the geometry. We have achieved a relationship between these displacements. What is xa minus xb? Is half times, so let me just strike off 2 here, this is half, so 1 by 2 delta xa minus delta xb plus yb minus ya is a positive quantity which is root 3 by 2, right, times delta yb minus delta ya. Again I will reiterate, this can be used for any configuration, whereas this can be used only for this right angle configuration, okay. So you have to make that distinction when you do this, okay. I already know delta xa equal to 0, so I can erase it. Now this relates delta ya to delta xb and delta yb, okay. The net result will be delta ya yb equals, I will get something in terms of xb and yb. I already have what is delta xb, if I substitute here I will get in terms of delta ya. And what is this you are getting? This half and this 2 goes off, I get it as half of delta y. Let us see if it is reasonable. Let us go back to this. If I move this a little bit, what should be the movement here? Will it be same as this? The answer is no, this will be less than this. How much less? Perhaps as I move towards C, the total y displacement is equal to 0. So halfway I should get half the displacement that I have gotten here. So roughly I have a mental picture of, oh, okay, delta yb is half of delta ya, seems alright. Okay. Now going back to this particular problem, do I need delta xb? The answer is no, because I need to get only the values of delta yp and delta yq. For that I do not need x, alright. How do I find out delta yp? I averaged, since it is at center, I average delta ya and delta yb. I will get for this. I will average delta yb and delta yc. Delta yc is 0, and therefore delta yb by 2 will be automatically delta yq. Okay, so that is what I am going to do next. Delta yp is equal to, since it is midway, delta ya plus delta yb by 2, and that is equal to delta ya plus half of delta ya divided by 2, and that is 3 by 4 delta ya. Alright. Similarly, I can find out delta yq, which is nothing but delta yb by 2. And what is delta yb by 2? It is equal to delta ya by 4. Now if you look at it, delta yp is written in terms of delta ya. Delta yq is written in terms of delta ya. So when I now write down the entire virtual equation, I will find that I would have written all of them in terms of delta ya. Okay. Let us just finish that particular exercise, we will go back to that. Let me just write down clearly what we obtained. We got applying delta ya, we get delta yp equal to 3 by 4 delta ya and delta yq equals 1 by 4 delta ya. Why did we look at delta ya, delta yq? Because those are the active forces for which we need to find out. Okay. And what is the direction of these? This is upward direction, this is upward direction, because they are positive notions. Okay.